Now, when we look at types of magmas, right, all magmas have silica. And remember, whenever we look at silica, we're looking at SiO2, some combination of SiO2, silica, right? And besides silica, there are other components like aluminum oxide, calcium oxide, sodium, potassium, iron oxide, magnesium. Those are some of the major elements. There's also titanium and some other trace elements, but mostly we're looking at these as the major elements. But the key one here is the composition of silica. In fact, when we look down here at our rock types, ultramafic, mafic, intermediate, and felsic, note that we're doing it based on the concentration of silica. So these are some of the numbers your book has. You'll see in one of my videos I have a little bit different numbers, but you can see the general range that we see, right? Ultramafic rocks are going to be less than 50%, right? Less than 45%, really. Mafic rocks are basalts are going to be about around 50, 52%. Intermediate rocks like andesite are around 60%, and felsic rocks are going to be more than 66%, right? Now, other things we want to point out here, your book makes a point of using these terms called dry magma versus wet magma. So remember, dry magma has no volatiles, Wet magma, these are the presence of volatiles, up to 15%. Remember, the key volatiles are H2O and CO2. Now, what happens to these magmas, right? So they're going to move through the crust, and eventually they're going to solidify. They're going to make a rock, right? And so why are these magmas moving? For two reasons. Buoyancy, the magma is less dense than the surrounding country rock, and then the weight of the overlying rock creates pressure at depth that literally squeezes this rock upward, right? It squeezes that magma upward. And then the other thing we should point out is this idea of viscosity. Viscosity is the clumpiness or stickiness of the magma. Viscous magmas tend to be very thick and move very slowly. And that viscosity depends on silica. So the more silica, the more viscosity. So that means felsic magmas tend to be viscous, right? Whereas mafic magmas tend to be more fluid, and they flow farther from the volcanic vent, or they can move more easily. When we start talking about volcanoes, I want to talk about this idea about silica polymerization. Remember, a polymer is like a fabric, a linking of molecules. So when you have more silica, you make more links. I always think of polymerization like Velcro. So the silica has these Velcros, so the Velcro starts sticking to each other and makes the magma kind of stiff. Now, when you're thinking about making this magma into a rock, well, your book uses the word freezing. And I usually use the word solidification or crystallization, because as the magma cools, it's going to form mineral phases, crystallization, and it's going to eventually solidify into a rock. But your book uses the term freezing. And again, as a rock freezes or solidifies, it's going to start, as it moves upward through the crust, it's going to start losing volatiles, because the volatiles will escape more easily. And when the volatiles escape, remember, the volatiles help break the chemical bonds. Well, if the volatiles are gone, the chemical bonds form, and you start making the rock, right? Freezing temperature rises. And then also, as these magmas move up through the crust, they're going to experience lower temperature. The thing we have here are these cooling rates. Right, so a cooling rate depends on how fast the magma can transfer heat into its surroundings. And we know that rock is a very good insulator. It's a poor conductor of heat. And so the cooling rates really depend on three factors. The depth of the intrusion, right? The deeper it is, the hotter it's going to be, the longer it's going to take to solidify. The shape and size of the magma body, right? So in fact, your text has a pretty good example of this one, showing that smaller magma bodies will have larger surface areas, and they'll cool faster, whereas a larger body will have a smaller surface area and take longer to cool, right? Kind of a pancake shape structure, magma will cool faster because it has more surface area than a volume that's equal but in a round shape, right? So that also dictates the rate of cooling. And finally, the last bullet here is if there's any groundwater circulating down there, because that'll cool the magma as well. Now the next part here deals with this idea of fractional crystallization. Now, the key thing I want you to point out with fractional crystallization is if you have a pie, you're going to cut the pie into different segments here, right? So when I cut the pie into segments, that's called fractionation, right? When I cut the pie into segments, that's called fractionation. And so basically think about fractional crystallization as a separation, because if I take one of these pieces out, it's a separation, right? So in other words, I'm removing components from the original magma in this case, right? So molten rock contains many different chemical compounds. Each of these compounds form at different freezing temperatures, right? And so there's a definite sequence of crystallization. There's a definite sequence of crystallization. So it starts off with, so we can think of this as high temperature over here. So high temperatures, like olivine, right? Olivine is an isolated silicate structure that forms at high temperature. Then the pyroxenes, the single chains, then the hornblends, then the micas, and then eventually you get to the framework silicates, which are the feldspars and the quartz, right? And so these would be usually at lower temperatures. The only one that doesn't really fit this sequence are the plagioclases, because plagioclases are forming at pretty high temperature. But let's look at figure 4.7 here. And so that's this little figure down here, which also shows this crystallization. So as minerals start forming in the magma, right, some of these minerals, because they're in a liquid, start to settle and sink out of the magma. And the residual magma up here becomes more felsic, right? So, in fact, I have two words I want to add here. So the minerals that accumulate down here at the bottom of the magma chamber, I call these cumulates. Cumulate. So the cumulate occurs down here at the bottom of the magma chamber, whereas this residual magma up here is called the residua. So there's residua, which is the residual magma. It becomes more felsic because I'm removing some mafic components, right? And so that allows the chemistry of the magma to change over time. Now, the next thing I want to do is I want to talk about this idea of Bowen's reaction series that your book talks about, but I have a different figure I want to point out here. So we'll look at my figure in terms of Bowen's reaction series. So as new crystals form from magma, they extract certain chemicals preferentially from the melt. And so that means the residua is changing chemistry. Residual magma becomes more felsic, right? And so in this case, there are two branches I want you to note here. Note that in this branch over here, we have from the isolated structure olivine to the single chain pyroxene to the double chain amphibole to the sheet silicate biotite. So here, there's actually a change in the silicate structure as you're going from higher temperatures here to lower temperatures. So we call this branch over here, we call this the discontinuous branch. Now, on the other side, note that we have only one mineral, the plagioclase feldspar, going from higher temperatures to lower temperatures. But note it starts as calcium-rich to a sodium-rich, calcium-rich to a sodium-rich, right? And so we call this the continuous. So there are two branches, the discontinuous branch and the continuous branch. And then note that as we get to even lower temperatures, we start forming potassium feldspar, muscovite mica, and finally the last thing to form is quartz, right? Now, if we think about shapes, usually up here, these minerals are going to be euhedral. In other words, hedral means a shape, and U means true. So true. So when you look at these, they're going to have their true crystal faces. All the sides of the minerals are going to show up here, right? We're going to have these crystalline structures, very obvious, right? When we get to these intermediate magmas or intermediate temperatures, here we're going to see a subhedral, and all that means is only we may see one crystal or two crystal faces. Then there's a room problem because these minerals ran into other minerals that were kind of crystallizing next to it, right? And so they're going to be, so we see maybe 1 or 2 crystal phases, not the whole thing, because again, we're starting to run into a room problem as more and more minerals, more mineral phases begin to solidify, crystallize from the magma. And finally, at the very end, the minerals that form at the lowest temperature, especially quartz, they're going to be anhedral. And all that means is without crystal shape, right? So there's going to be minerals in the magma here, right? That formed at higher temperature, and then the quartz will be minerals that will form at the very end, and so they're just going to form in whatever space they have available to them. So they're just going to fill in these cavities in here, and if I could extract that guy and take a look at it, it'll just be kind of like a little blob in there with no crystal shape, right? Anhedral. So when we look at rocks, you can often tell which minerals formed at higher temperatures because they usually have euhedral structures. The ones that formed at lower temperatures are going to have the anhedral structures.